Greetings, calculus students. This is Mr. Meyering coming to you from cyberspace. Just wanted to go do a quick video on Q theory. What is it and what we'll be doing with it? So we'll be looking at the Q theory basics. So real fast, what is Q theory? I've given a few insights to it. Maybe you've heard about it before, but essentially, it's all sorts of things. It's a bunch of lines, really. So here's a bunch of people waiting for the latest, already out-of-date Apple iPhone. Here's some people trying to get their groceries. They're in a line. Here's some people waiting to vote. Very good citizens there trying to vote. And then finally, here's some people that waiting to find out that they don't have any talent. So it's all about lines and the mathematics of it, how long it takes, how long is the line, how long is the service. I mean, anything mathematically you could calculate with lines and then analyze it. That's what Q theory tries to do. Many examples of Q. Bank customers in a long line waiting for several people. Pizza delivery orders when they come in and when they go out. When you gave blood at the blood drive. Product assembly line is a type of queue. Customer service hotline when you're waiting on hold, you are in the queue. Or cars waiting at a ramp meter trying to get on the freeway. That would also be considered a queue as well. So lots of different types of examples. We're going to be looking at a specific example and we'll get to that in a second. So essentially, what can we do with it? If we're going to create a mathematical model of a line, what sort of data would you collect? And what sort of questions would you want your mathematical model to answer about that line? And so when you think about that, that's the stuff that I've mentioned already. It's just the basic things. And so here's pretty much what we look for. So what do we want to collect? How many people got in line? How long did each actual service take? So not how long did, so service is different from wait time, and that's the third thing. How long did people wait in line? Service time is actually, in the service, so getting your food, checking out, stuff like that. What sort of questions would you want your mathematical model to answer about the line? How long did people wait on average? How long is the line on average? What are the odds the line is empty so that your server is available to do others? Or how long is the service time on average? Trying to figure out if you could improve it. So these are things that as a business owner, as an engineer, or as anything that deals with lines, these are answers you would want to know to try to figure out what you could improve. So, as I said, we'll be looking at a very specific example. So, these are the assumptions that we need for our work. First of all, no more than one arrival can occur at a given instant. So not groups, they all have to be one independent, which means arrivals and services are independent of each other, so your service time doesn't depend upon when you arrived. Arrival times and service times are modeled by the exponential distribution we've discussed, that probability density function. There's only one server in the system, so that's very important. So not like a bank teller line where there's a bunch of different people, not like the lunch lines here. So only one server. There's no limit on the length. That needs to be there in order for the exponential distribution to be accurate. We're going to use the Greek letter lambda to represent the arrival rate, arrivals per time unit, whatever you determine that would be. Could be minutes, days, hours. The Greek letter mu, mu, is the service rate, customers served per time unit. So based on that same time interval, how many customers were served. So those are the assumptions for our mathematics to work, and that's important for you to remember as we continue on with our next videos that introduce all of the calculations and the formulas for Q theory.